Okay. Hopefully everybody had a chance to see the video from Thursday. Yes, Thursday. Um, if you didn't, you might be kind of lost for today, but in short, we covered methods for qualitatively assessing the acidity of different compounds or different protons on those compounds. Um, so today's molecule of the day is glutamic acid. This is the structure of glutamic acid. So it's got two carboxylic acids, right, one on the left, and then an amine. And so these two carboxylic acids are chemically different because one of them at the position next to the carbonyl has an amine, and then the other one at the position next to the carbonyl does not have an amine. So that tells us that those two hydrogen atoms on the carboxylic acids are going to be of different acidities because they're different. And then, well, I mean, I've already highlighted the one that's the most acidic, but you could also say, okay, what about the NH2? What about those protons? Could those possibly be the most acidic? And then you've got a whole bunch of just alkane hydrogens on that carbon and on the other three carbons that are sort of in the middle of the molecule. And so those are also protons that you'll have to look at and consider. So the mnemonic for assigning acidity is ARIO. So atom, resonance, induction, orbital. So first is look at the atom. Fortunately, in this case, we've only got carbon, nitrogen, and oxygen, and hydrogen, of course. But as far as big atoms go, carbon, hydrogen, and oxygen. So there's our periodic table. And we've got hydrogen atoms that are on carbon, nitrogen, and oxygen. All right. So these are all in the same row. And that means that the most electronegative element is going to prefer to have a negative charge in the conjugate base. So, you know, at sort of the end, we're looking at that oxygen. And so that means that the protons that are on oxygen are going to be more acidic than the protons on nitrogen, which are going to be more acidic than the protons on carbon. Okay, so we can automatically eliminate all of the hydrogens in the molecule except the two OHs on the carboxylic acids. Again, it's called the carboxylic acid, so I don't think it's a big surprise that their protons are pretty acidic. Okay, so that takes care of atom. AR, IO, R is for resonance. And so then we have to look at resonance stabilization of the conjugate base of each of those acidic protons. So we're looking at resonance stabilization of this conjugate base. And then I haven't drawn the other one as a conjugate base, but imagine if that hydrogen were not there, we'd have a conjugate base over there, and there's resonance stabilization all throughout that carboxylic acid. And so both of the conjugate bases are resonance stabilized, so that that resonance does not give us a decision. I is for induction. And so now we're going to look for electronegative atoms that are in the vicinity of the conjugate base. And well, in the example that I showed you in the video, I was using chlorine or really any halogen. But in this case, right, we have here a nitrogen, which is more electronegative than carbon. I mean, very, very slightly. And so that means that there is a little tiny bit of inductive stabilization due to this nitrogen on this side. But for this one, right, we don't have that. We don't have a more electronegative atom. Really, we just have hydrogens, which are not electronegative at all. And so there's a tiny bit of inductive stabilization on that side of the molecule. And so that means that the proton on the right is the most acidic. And so that's the conjugate base that we're going to have. So if you treat glutamic acid with sodium hydroxide, you get the conjugate base of glutamic acid, which is glutamate. And if you use sodium as the cation, you get monosodium glutamate, MSG. Okay. Unsurprisingly, I've picked sodium hydroxide in this case because I wanted to make MSG. But you could use any base that is strong enough to deprotonate a carboxylic acid to do this reaction. You just might not get MSG specifically. So let's talk about that. Let's talk about choosing reagents for acid-base reactions. Really any reaction in general, but mainly acid-base reactions. So here's sort of a general equilibrium acid-base reaction. And then here's another one. And these are really only differing in the charges on these fictitious molecules A and B. And so what we need to do in order to sort of select actual reagents rather than just A and B is we're going to look at the ions that are part of the acid-base reaction. Now, it's not unusual for mm, for us to write the counter ion, so the ion of opposite charge, because ions always exist as pairs, positive and negative. But it might be that in this case we really don't care about Z or really don't care about X. But regardless, we're going to focus on the ions in the reaction. And the equilibrium, shown by the equilibrium arrow, favors the more stabilized ion. And that goes back to ARIO, atom, resonance, induction, orbital, to figure out which of those ions is more stable. And so all we have to do to choose and that makes it sound easy. It's not easy. But all we have to do is pick an acid or base, or could be another reagent, but we'll mostly talk about acids and bases. Choose a reagent that pushes the equilibrium the way you want it to go. So let's say we have an acetate ion in our solution, and we want to protonate it to make the acetate into acetic acid. Um, so let's see. Well, water can act as an acid or a base. acid or base. But let's see, can we use water to protonate the acetate ion? So what we should do is write out that reaction and look at the equilibrium. So we have our acetate and water. There's our not totally drawn yet equilibrium arrow. And then we'll assume the reaction works. And water will be our acid, acetate will be our base. And so base is a proton acceptor, the acid is a proton donor. And so we'll do that reaction. There we go. We've transferred a proton from the acid to the base. So that means this is our conjugate acid. And that's our conjugate base. So there's two ways that we could go about determining which side the equilibrium will lie on. The first is to look at the pKa table. And when using the pKa table, we'll compare both of the acids. And we'll look for the pKa values of water and the pKa value of acetic acid, compare those, and whichever is the weaker acid, the equilibrium will lie on that side. That's the first way. The second way is to use ARIO. And when we use ARIO, we're looking at the conjugate bases, or well, both of the bases. And so we'll look at the bases in the ARIO method and say, okay, which of these is the most stable conjugate base? The equilibrium will lie on that side of the reaction. So okay, so if we look at the acids, the equilibrium lies on the side of the weaker acid. With the more stable base. Okay, let's do well, we're going to get the same answer, but let's look at pKa first. So if we go on the pKa table, we can look up the pKa's of water and acetic acid. So let's do that. pKa's. All right, water is 15.7. Okay, right here. Sorry. And acetic acid. Do I have acetic acid? Yes, I do. Acetic acid right there is 4.75. All right. So which is the weaker acid, water or acetic acid? Low pKa means stronger acid. So the higher pKa is the weaker acid. So water is the weaker acid. And that means the equilibrium is going to lie on that side of the equation. Okay, so this is going to, so the answer is no, water is not adequate for protonating acetic acid because if that reaction occurs, well, it's just going to go backwards and stay that way. But let's do the REO method just to make sure. So we'll look at the bases instead and find the more stable conjugate base. So atom resonance induction orbital, atom. Okay, so the negative charge on the bases is on an oxygen in both cases, so we can't use atom. Resonance. Here we go. So we can draw a resonance structure of the acetate ion, right, where we do that. But for hydroxide, the other base, there's no resonance structure that we can draw. So that means that acetate is the more stable base, and the equilibrium lies on the side with the more stable base. Yeah, okay, so that agrees with what we said earlier. So water is a no. I don't think that was a big surprise. Water's generally not a very good acid. Somebody give me another acid that you would think would work better than water. Name one you've used in the lab. HCl. Let's try HCl. Okay, so we write our equation again with HCl. Okay, so acetate plus HCl gives us acetic acid. And then the conjugate base of HCl is going to be Cl minus. Acetic acid is our conjugate acid. Chloride is our conjugate base. Okay, so for pKa, we need to look at the acids. So HCl versus acetic acid. All right, acetic acid, the pKa is 4.75. HCl, do I have HCl in here? I do. Wow, look at me. pKa of HCl minus 7. All right. Lower pKa means stronger acid. Higher pKa means weaker acid. So that means acetic acid is the weaker of the two acids. Equilibrium lies on the side of the weaker acid. There we go. Okay, so this reaction should go forward. So it looks like this is going to work. All right. For REO, we look at the bases. Atom, resonance, induction, orbital. Okay, first is atom. All right, so we're comparing acetate with the negative charge on oxygen and chloride with the negative charge on chlorine. So oxygen and chlorine are, well, they're not in the same row or the same column. Now, I'm not going to test you on which of these wins. And so, you could say that it could kind of go either way, oxygen versus chlorine. I mean, we've already determined the answer to the problem, so it ends up not being a huge issue. So if we say, all right, let's ignore A for Ario, then we could look at resonance. And okay, you can see where this is going. Acetate ion does have a resonance structure, and chloride does not have a resonance structure. All right, so that means that the acetate is that's going to screw us up, isn't it? Yeah, it is. Then what I'll say is if you run into this problem where you end up not being able to compare directly um, in the rows versus the groups or columns for the atom part of Ario, then we need to use the pKa method where we look at the acids. Okay, so this extends not just to choosing reagents where, we're picking an acid to protonate a base or a base to deprotonate an acid that works the same way. It also relates to solvents, interestingly enough. And this causes something we call the leveling effect. This mostly has to do with bases. And the leveling effect says that the base we use cannot be stronger than the conjugate base of the solvent that we're doing the reaction in. Yes.
For the example that we use it, I have a question, like,
Yes.
if I get my PKA and I don't determine like which one is the weaker one, like do I have to go and do the AR?
No, you don't, and it's probably just easiest to use the pKa table, unless it's a molecule that's not in the pKa table, and then you'll have to use the other method.
And it doesn't work at all.
Correct. Yep. Yeah. So, good question. Only one of these methods is necessary when you're doing these problems. The pKa table is going to be easier because you're literally given the values. But if you have a more complicated molecule that doesn't look like anything that's in the pKa table, then you'll need to use Ario. So let's say that we've done some of this analysis up here, and we've decided that we need to use a very, very strong base for our reaction. This is an example of a very strong base. It's called N-butyl lithium. And well, if you compare it to something like hydroxide, which we think of as being a strong base, one thing you could do is look at the conjugate acids, and this is using the pKa method. You can look at the conjugate acids of these, water and butane. And the pKa of water is 15.7. And the pKa of butane is like 50. It's very high. So a stronger acid has a weaker conjugate base, and a weaker acid has a stronger conjugate base. So between water and butane, the conjugate acids of the things we're comparing, water is the stronger acid. So it's going to have a relatively weaker conjugate base. I know it sounds strange to say that hydroxide is weak, but we're in the big leagues here. So hydroxide is nothing. All right. For n-butyllithium, where the conjugate acid has a very high pKa and the conjugate acid is a very weak acid, right? It's butane. It's not an acid. So that means the conjugate base is going to be an extremely strong base. Okay. So thank you. Let's say we need to use this base, and we were like, okay, well, let's use water as our solvent for this reaction and use butyllithium as a strong base. I'm just going to draw the butyl anion. So we put our butyllithium in water, and this is going to be just like this kind of thing up here, where we need to compare, and essentially we need to make sure that water is not a strong enough acid to protonate the base. Okay, so in the same way that HCl, nope, where was it? Yeah, in the same way that HCl was a strong enough acid to protonate the acetate ion, we want to make sure that isn't the case here, because otherwise we're going to have a reaction between our base and our solvent. Okay?
You got rid of the lithium.
I did.
Would it make a difference if we kept it in there? Or is it just
No, because it's just going to float around. Actually, I'll draw it in at the end after I Okay, so there's the products, and what we could do is just say, all right, well, the lithium is Li plus, and so that has to hang out with our negative charge wherever it goes. And so that means that our OH minus is actually in the form of lithium hydroxide. Okay. So, well, we've really already done this whole business here. Okay, there's our two acids. We should label our base and acids. Okay. There we go. And the equilibrium is going to lie with the weaker acid, so the higher pKa. And here we've got like a massive, ridiculous difference in between those two pKa's. And so our equilibrium is going to lie way to the right. So what that means is if you have your reaction in water and you add butyllithium, well, it'll explode, but mostly because of this reaction, right? You're going to produce the conjugate acid, which is butane, which at the temperature that this gets to is a gas, and so that blows your apparatus apart. And a nice stable conjugate base in the form of hydroxide, lithium hydroxide in this case. So okay, obviously this is a big problem because we would really like to use water as a solvent for as many reactions as we can. But if you need a base that is stronger than the conjugate base of your solvent, so if we need to use a base stronger than hydroxide, you cannot use water as a solvent. Very inconvenient, but a very common problem. Okay, in water, no base. Stronger than hydroxide can be used. Okay, so some other solvents that we can use for things like butyllithium would be, well, hexane. And in fact, this is the solvent that your butyllithium is supplied in. The problem with hexane is it's really, really non-polar. Water is really, really polar. And so we would like something of intermediate polarity. And that comes in the form of this 5-membered ring with an oxygen. Which is called tetrahydrofuran, or just THF. And this is the classic solvent that is used in reactions with extremely strong bases because it doesn't have a proton on the oxygen. If it did, that would make it a pretty crummy solvent for this reaction because that hydrogen would be pretty acidic, right? OH protons are pretty acidic. And the only other hydrogens that it's got are, these guys on the carbons, which are not very acidic at all. And this molecule is fairly polar. It's got the oxygen with its lone pairs on one side, and then it's got the hydrocarbon part at the bottom. And so that kind of enables it to dissolve some polar molecules. So that's how you can get polar molecules with a really strong base. So this is something that we won't even do this in organic 2, like in the laboratory, but there is an example of the leveling effect that you probably saw as early as Gen Chem 1 lab. And that is, well, we just talked about bases, but the same is true for acids. This is one of those places where I'm going to reveal a lie that has been told to you. I like doing this, although it's kind of sad sometimes. Okay, so what's an acid that we might want to use in water? How about sulfuric acid? Okay, we can do that, right? Sulfuric acid in water. But let's pretend that we don't know what happens. And write an acid-base reaction for this, where sulfuric acid is the acid and water is the base. Okay, so Don't let now we're sort of in inorganic chemistry land and not organic land, but that's okay. The definitions are the same. The acid donates a proton to the base. Okay, so if we take H2SO4, remove H plus, we get HSO4 minus. That's the conjugate base. And then the conjugate acid of water, well, we know that that's H3O plus. Okay. So we need our pKa's. So the pKa of sulfuric acid up here at the top of the pKa table is -9. And then the other acid is hydronium, H3O plus, and that has a pKa of -1.74. Okay, don't let the negatives mess you up. We want to go, the equilibrium is going to lie on the side with the weaker acid. The weaker acid has a higher pKa, and so the weaker acid is what? Is H3O plus. Okay, so the equilibrium lies over there. So what does this mean about sulfuric acid in water? Is that it's not sulfuric acid in water. It's H3O plus. Now, that's assuming you have a 1-to-1 mole ratio. If you have just this very small amount of water, then you won't be able to do this reaction for every molecule of H2SO4. But because sulfuric acid is stronger than the conjugate acid of the solvent, in dilute sulfuric acid, we don't get that really strong -9 pKa. Instead, we can only have the conjugate acid of the solvent, H3O plus, which only has a pKa of -1.74. So we lose we only get one millionth of the acidity of sulfuric acid when you dilute it with water. And so that means that this here so when we have aqueous sulfuric acid, H3O plus is the actual acid that we're working with. And so when I'm talking about acidity here, I'm talking less about concentration because, yeah, of course, you can have different molarities of sulfuric acid, but the molarity of the acid doesn't affect the types of molecules that it can and cannot protonate. So, of course, this is a very, very different example, but if you're making a comparison versus one acid-base pair and another acid-base pair, and you're trying to figure out what molecules sulfuric acid can protonate, if it's diluted with water, you're only going to be able to protonate bases whose conjugate acids have a pKa down to -1.74, not all the way down to -9. If you want to do that, then you need concentrated sulfuric acid with no water. Lab tips. Anyway, so that's the leveling effect. The base can't be stronger than the conjugate base of the solvent. The acid can't be stronger than the conjugate acid of the solvent. Okay. Some of y'all got me ahead of the cart in front of the horse, which is not a bad thing. But we need to talk about counter ions. So the lithium in the butyllithium example. This is mostly going to have to do with bases because our bases are the ones that are more commonly charged. It works for both. So these negatively charged bases that are floating around always have associated with them, whether we draw it or not, a cation, right? Anion has to have a cation has to have an anion. And so this is going to be called, you probably remember it being called a spectator ion. In organic, we usually call it a counter ion, but neither term is wrong. And so we've seen an example, but let's see another. I should have picked one where the typical ion is not sodium, but it's still going to be sodium. Oh well, I love sodium. So this is kind of what the acid-base reactions I've been drawing for you look like. Typically, we have a charged species on both sides, and it's naked. But what this reaction actually looks like, if we were to draw it out in more of a Gen Chem style format, would be like this. So I think we can see what has been added here, right? We've added a sodium. And the sodium is associated with the anion on both sides of the equation. Okay. Pretty logical, I think.
Just add sodium.
Yes, I randomly decided I was going to use sodium as opposed to potassium or rubidium or any other metal on the first row because we got to have a +1, can't have a +2, or else we got to have multiple equivalents and stoichiometry starts happening. However, what's more difficult is going the other direction, starting from an equation like that and trying to see what is a spectator ion that isn't important and what is. So let's do. Right. As a quick reminder, phenyl is just a benzene ring. So that means that this reaction looks like this. Nope. Sorry. Okay, so that's just expanded our condensed formula and our abbreviations into a skeletal structure. But we still, I mean, this example is on the simple side, so maybe you can still see what's going to be the conjugate acid in the acid in the base, the conjugate base. But we don't have any ions, right? It didn't look like it, but they've been written so that the cation and the anion are together. Okay. And so, for example, potassium hydroxide, KOH, right? That's an ionic compound. You remember at the beginning of Gen Chem where they would give you a molecular formula and you have to tell whether it's an ionic or a molecular or covalent molecular compound. So KOH is K plus and OH minus. And there's our other set of ions. This is a very common way to write this sort of, in this case, it's benzoate. But any carboxylic acid salt is just to write the metal cation on the oxygen, just like it's a hydrogen. And so I know that sounds like a method devised intentionally to trick you, but it's not. It's just so we don't have to write the negative and the positive charge. So one of the keys is going to be looking for specifically those metal elements and saying, that has to be a cation. And so whatever it's attached to has to be an anion. And now we can see that we've got hydroxide. So that's going to be our base. And our conjugate base on this side is going to be this benzoate anion. And so the other way that we might write this reaction is just without the potassium. Like this. And now we can more easily see what's an ion, what's not an ion, what's an acid, what's the base. And then we can do, whatever equilibrium predictions we want to do. Like that. It's going to look like that. And these are just the potassium or the sodium or whatever. Usually it's potassium or sodium. Sodium is the most common. We just emit them because they're spectator ions. They don't do anything in the reaction. But for example, when you're going into the lab to do an experiment, you can't just open up a bottle of OH minus and add it to your reaction. It didn't work like that. You have to have potassium hydroxide or sodium hydroxide or something like that. Okay, so main thing there is look for those alkali metals Those will be your cations. Okay, one final point. So all of the acids and bases we've talked about so far, we've been using the Bronsted-Lowry definition, which was the acids are the proton donors and the bases are the proton acceptors. But there's a broader definition. So this is so this means that more things are going to start looking like acids and bases than previously. So a Lewis acid is an electron pair acceptor. Okay, don't let the fact that Bronsted-Lowry acids are proton donors, not proton acceptors. So there's a little bit of kind of looking backwards, easy to mess up here with your acceptors versus donors. And a Lewis base is an electron pair donor. Now, obviously, there's a big difference in between proton accepting and donating and electron pair accepting and donating. And in fact, there are a lot of Lewis acids and bases that are not Bronsted-Lowry at all. They don't do any proton transferring. So importantly, this does not require proton transfer, although it can have proton transfer. You will find, however, that often when you have a Lewis acid and base reaction, one of the components, at least one of them, looks like a classic Bronsted-Lowry acid or base. We'll look at an example. Before I tell you which one is which, I'm actually going to draw the mechanism. Okay. Strange looking reaction. Doesn't look like it would be favorable because you're creating these two charges right next to each other. But it actually does happen. And so, okay, BF3, you've probably never seen BF3 before, but NH3, that's ammonia. And ammonia is what, an acid or a base? Base, okay? So it's a Bronsted-Lowry base, because that's how we have thought of it of all acids and bases so far. But what about Lewis? Okay, so a Lewis acid is an electron pair acceptor. All right, so which of these two starting materials has accepted the electron pair? Well, that's the one where the arrow ends, because that's where the electrons are going to the acceptor, which is the Lewis acid, BF3. And so, okay, that's good. That means our other one has to be the Lewis base. And that's nice because in this case, ammonia, which we would know as a Bronsted-Lowry base, is also a Lewis base. Right, so one of them does kind of match up with what we expect. And Lewis base is an electron pair donor. Yes, ammonia is donating its electron pair to the boron to make this cursed-looking molecule. You'll notice there's only one curved arrow in this reaction. Right, that would not be the case with a proton transfer, where you have to have two arrows, at least two arrows. But for Lewis acid-base reactions, you almost always just have one arrow.
Will it be told like on the exam if it's what you want it to be, like if it's Reno Lewis one or the other one? Or yeah, no,
That's a good question. Default will be Bronsted-Lowry. Okay, because most of what we're talking about is all of right, this is the very last topic. So if I want you to focus on Lewis acid versus base, I will specify Lewis. And in fact, that's not just in this class, that's like for the rest of chemistry. Generally speaking, if you're talking about Lewis acids and bases, you have to say Lewis. It's not generally understood. Well, it is understood, but it's not assumed that's what you're talking about. Thank you. Good question. Let's do this one. Okay. I think you're seeing a trend that these reactions tend to look weird and give very strange looking products. That's not a fluke. And in fact, you should sort of get used to seeing, well, don't get too used to it, but get used to seeing these positive and negative charges right next to each other. We call this a Zwitter ion. But don't worry about that. This is often an indication that a Lewis acid-base reaction has occurred. Also, we're seeing elements that we don't usually see, right? Boron, boring. Aluminum, not a very common element, really, we think in organic chemistry. And there is a very strong correlation between these specific elements and, in this case, being Lewis acids. Okay, so I'm giving you the answer. But let's draw a mechanism for this reaction. So again, don't get scared of the aluminum. We're forming a bond between the oxygen and the aluminum, right? And those electrons are coming from the oxygen, right? Because the oxygen goes from 2 lone pairs to 1 lone pair. So the oxygen is going to be our electron donor, and the aluminum will be our electron acceptor, electron pair, donor and acceptor. One arrow, just one arrow. And that's going to give us our product. The oxygen has 3 bonds and 1 lone pair. That gives it a positive charge. The aluminum has to have the opposite. If you really wanted to nitpick this, you could go in and calculate the number of electrons. Don't worry about that. But based on our rules, a Lewis acid is an electron pair acceptor. A Lewis base is an electron pair donor. So that means that acetone is a Lewis base. Okay. When you think of acetone, I don't think you think of it being a base, right? Me neither. And aluminum trichloride is our Lewis acid. I'm not going to say all uses of aluminum trichloride. All uses of AlCl3 in this class will be because it's a really, really good Lewis acid. So equate these two, that compound with being a Lewis acid, and actually BF3 is the same. These are two very, very classic Lewis acids that are almost exclusively used for that purpose, because they're Lewis acids. Also, not a coincidence that boron and aluminum are in the same group in the periodic table. They can both form a sextet of electrons, so only have 6 electrons. I don't know if you remember that weird rule about boron. Applies to aluminum as well. And it's another reason why they're good Lewis acids, because they can have 6 electrons or they can have 8 electrons. And so, right, in this case, both the boron and the aluminum are going from 6 electrons, like 3 fluorines, 3 chlorines, no lone pairs on the, I almost said metal because I'm a weird chemist and I think boron is metal. And then in the products here, they have 8 electrons. Okay. But the main thing I want you to get out of this, of course, is that Lewis acids are electron pair acceptors and Lewis bases are electron pair donors. If there's a few things. Those are really the only good examples. Questions on Lewis acids and bases? Okay, in the last 10 minutes, is there anything on chapter 6 that you would like me to go over or come up with an extra, well, I say extra practice problem. Probably should have mentioned this before. Problem set 6 was originally supposed to be due next time, but somebody hasn't finished writing it yet. So I will probably upload that by Thursday, and then you'll have the break to worry about your homework. Sorry. But you'll have plenty of time to review it and work on it. Okay, questions? General questions? Yes.
You show an example with another ring, with another benzene.
Like
Like that.
a lot of them will have benzene rings, but most, if not all of the time, the benzene ring isn't going to have well, it's not entirely true. Yes. Okay, I have an idea now. Let's see. Okay. Okay, so which of these is the stronger at what actually, I should say uh rank acid strength. Okay, this is going to require RAO because if I'm correct, we do not have any sulfur on our pKa table. So we're going to need an alternate method to figure this out. Okay, so another thing that you should probably notice is we've got two that are OHs, and then the other is SH. And we've also got two that are cyclohexane rings, and one that's a benzene ring. Those are both going to be important. So A and REO is for what? Atom. So well, okay, maybe a dumb question, but we've got these hydrogens here all over well, they're really all over both rings. But we also have oxygen and sulfur, which are both more electronegative elements than carbon. And so we don't have to worry about the CH bonds. Okay, so all of those hydrogens that are not written are not going to be the most acidic. So we're only going to focus on the OH and the SH. Not acid. Atom is the first priority rule. And so let's see. ABC, which one wins the atom? C, because we're comparing oxygen with sulfur.
Same row before.
Same row. Same column. Yeah, I know this is what you mean. It's okay. Okay, oxygen, sulfur are in the same this thing group or column. And in that case, then we want to look for the larger atom, which in this case is sulfur. So this is the most acidic of the three compounds. Okay, what about A versus B? So we can't use atom. What is our next priority rule? Resonance. So I suppose we should have already done this, but we should draw the conjugate base of each one. For the atom rule, you can kind of get away without drawing the conjugate base. But I would strongly advise against trying to do the resonance rule without drawing the conjugate bases. We don't need to do the sulfur one, but whatever. Okay, for A, can we draw resonance structures of the conjugate base of A? So we move electrons from the lone pair down here, and then, we have a problem, right? This carbon atom there already has an octet. And so if we bring those electrons down, we'll end up exceeding an octet on that carbon. So there's no valid resonance structures of that ion. Okay, and so the same goes for the sulfur. Again, sulfur has already won the competition, so we don't really care, but same deal. Okay, what about the one with the benzene ring? Yeah, we can draw some resonance structures here. We can draw a lot of them, actually. I'll just do the first one, go down there, and then let me draw my bonds less ugly. There we go. And then this can go there. Okay, so that gives us that resonance structure. And there are yes resonance structures. Let's see, 1, 2, 3, 4, 5. 6, including the original one. But in this case, we have at least one, and that's all we need to know. So that means that the one with the benzene ring does have resonance stabilization, and so it's second most acidic. And then that one loses, and it is the least acidic, the least strong acid. Okay, see how we put both of the rules together to rank things? I probably won't ask you to do much ranking, and if I do, it will not be more complicated than this. All right, next time we'll start nucleophilic substitution reactions.